Welcome back to Iron Process, where we take you deep inside the world's most extreme engineering and industrial operations. Today, we journey into the Swiss Alps, where engineers are modernizing the massive 200B Hydropower plant by drilling a steep tunnel straight through solid mountain rock. Using a specialized tunnel boring machine, crews must overcome unstable geology, high water pressure, and brutal underground conditions to build an entirely new water conveyance system hidden deep beneath the Alps. This is more than tunneling. It is a battle between man, machine, and mountain. Join us as we go inside one of Europe's most challenging hydropower construction projects and witness the incredible engineering making it possible. In May 2019, at Lake Ridham in Ticino, contractor Marty began preparing one of the most challenging mountain construction sites in the region. Before excavation could even begin, engineers first installed a wastewater treatment facility designed by Allrad Technic. Because the site was located high in the Alps, the entire system had to be modularized into compact, transportable sections and flown into the mountain by helicopter. The plant processed drilling, slurry, and tunneling wastewater before releasing treated water back into Lake Ridham, preventing contamination during underground excavation. The project itself formed part of a massive modernization program for the Ridham hydropower plant, operated by SBB, the Swiss Federal Railways. For more than 100 years, the facility has supplied power to the Gotthard railway line, one of Europe's most strategically important transportation corridors. The Gotthard route is far more than a normal rail connection. It is a critical freight and passenger artery crossing the Alps, transporting enormous volumes of cargo between northern and southern Europe every day. Moving heavy trains through steep mountain terrain requires a power system capable of delivering exceptional reliability under constant demand. After more than a century of continuous operation, engineers concluded that maintaining the original infrastructure was no longer enough. The entire water conveyance system needed to be upgraded. The core of the project involved replacing the aging surface pipeline with a completely new underground pressurized water tunnel excavated directly through the mountain itself. But the geology above the planned alignment presented a major problem. The overlying rock strata were weak, fractured, and heavily saturated with groundwater. To reach more stable geological formations, crews first excavated an access tunnel before beginning work on the main inclined shaft using a specialized TBM with a diameter of approximately 3.23 meters. The new hydraulic tunnel system would ultimately connect Lake Ridham directly to the power station through an integrated underground network consisting of a lower pressure tunnel, an inclined shaft, an underground valve chamber known as the Schieberkammer, and a connecting tunnel extending back toward the lake. According to contractor Marty, the upper section measuring roughly 150 meters and the lower section of approximately 650 meters were excavated using conventional drill and blast methods. The central section, however, would require a gripper TBM capable of climbing deep into the mountain. In the early construction phase, crews advanced the lower pressure tunnel through drill and blast excavation. After each detonation, broken rock was removed from the tunnel, while workers stabilized the surrounding walls using shotcrete and steel support frames in weaker sections. But conditions underground quickly became far more difficult than expected. As excavation advanced through fractured geological formations, groundwater continuously poured through fissures in the rock mass, complicating both drainage and tunnel stabilization. According to the original plan, engineers expected to carry out nearly 250 blasting rounds, involving more than 20,000 drilled holes before reaching stable rock conditions. Then the project encountered a major crisis. As excavation approached an area geologists had predicted would be more stable, high-pressure groundwater suddenly erupted into the tunnel face after a blasting round. Water under pressures reaching nearly 10 bars violently flooded the excavation zone. Work stopped immediately. Probe drilling soon revealed the tunnel had intersected a heavily fractured rock formation containing an enormous volume of pressurized groundwater, with inflows reaching up to 100 liters per second. The danger was now extreme. Flooding, tunnel collapse, and instability inside the mountain threatened to halt the entire project. To regain control, contractor Marty abandoned normal excavation operations and switched to emergency ground treatment using a grouting curtain system designed to seal the water-bearing fractures ahead of the tunnel face. Engineers implemented a hybrid injection process specifically developed for unstable groundwater-rich geology. At the tunnel face, crews first installed a temporary concrete plug to prevent injected material from flowing backward during high-pressure operations. From there, workers drilled fan-shaped boreholes deep into the surrounding rock mass, creating grouting curtains approximately 20 meters long. Excavation could then proceed only around 15 meters before the entire treatment process had to be repeated again. The hybrid injection system combined two separate materials. Cement grout was first injected into smaller fractures to strengthen and seal the surrounding rock structure. When larger cracks carrying strong groundwater inflows were encountered, crews switched to polyurethane resin, or PUR, capable of rapidly stopping water penetration inside the mountain. Once the major inflows were controlled, cement grouting resumed to reinforce the remaining fracture network throughout the rock mass. Slowly, the unstable water-bearing zone began to stabilize. In total, crews carried out 14 separate grouting curtain operations involving nearly 1,000 boreholes, before finally pushing through the groundwater zone. The delays were enormous. By this stage, the construction schedule had already fallen nearly a full year behind the original plan. But eventually, groundwater inflow was brought under control, and the project could finally move into its next phase, the installation of the TBM. With the groundwater crisis stabilized, the project transitioned into its most critical phase, mechanized excavation through the heart of the mountain. But this was not a standard tunnel. The next stage required a TBM specifically engineered for steep gradient excavation inside fractured alpine geology. Unlike conventional horizontal tunnel boring machines, this system had to operate on an extreme incline of around 26 degrees from the very start, inside a confined underground launch chamber carved directly into the mountain. Because of its size and complexity, the machine could not be delivered as a single unit. Instead, it was transported in multiple heavy components and assembled piece by piece inside the tunnel itself. Using hydraulic jacking systems, engineers slowly pushed the nearly 100-meter-long machine up onto a specially constructed launch platform, aligning it precisely for steep gradient operation. After approximately 3 weeks of assembly and calibration, the TBM was finally operational inside the mountain. This marked the transition from drill and blast excavation to continuous mechanized tunneling. At the cutting face, 23 massive disc cutters rotate under extreme pressure, grinding directly into solid alpine rock. As the cutters penetrate the formation, the rock is fractured into chips and fragments, which are immediately collected behind the cutter head. From there, material is transferred into a dedicated chute system, where water is injected to form a slurry, allowing it to flow naturally downhill through the tunnel alignment. To maintain continuous forward movement, the machine relies on a hydraulic thrust system, capable of generating approximately 500 tons of force. These thrust cylinders push the TBM forward in controlled cycles, while the gripper system anchors against the tunnel walls, stabilizing the entire machine during excavation. But at Ridham, thrust was not the biggest challenge. The real problem was gravity. Because the tunnel is inclined at up to 45 degrees in certain sections, the entire machine is constantly under the risk of sliding backward under its own weight. To solve this, engineers equipped the TBM with a specialized anti-backsliding system known as Rückfahrsicherung. This system is based on a self-locking geometric mechanism. If backward motion is detected, the grippers instantly tighten against the tunnel walls, locking the machine in place. This safety system becomes absolutely critical in cases of hydraulic failure or power loss, where uncontrolled movement could lead to catastrophic failure inside the tunnel. The TBM operates in controlled excavation cycles. Each cycle advances the machine approximately 1.2 meters. First, the cutter head excavates rock. Then the machine anchors itself using grippers. Next, hydraulic thrust pushes the system forward. Finally, the trailing backup gantries are pulled ahead to support the next cycle. Behind the cutter head, a full production chain extends deep into the tunnel. Electrical systems, hydraulic pumps, control units, ventilation, and material handling systems are all integrated into a continuous mobile infrastructure stretching hundreds of meters. This is not just a machine. It is a moving industrial system operating inside a mountain. While the TBM advanced the incline tunnel, a second major excavation was taking place in parallel. The underground valve chamber, known as the Schieberkammer, was being constructed using traditional drill and blast methods. This enormous underground cavern would house the main control valves responsible for regulating and shutting down water flow during hydropower operation. Because the chamber was located close to the Rittm Dam, every blast had to be carefully controlled. Even small vibrations could potentially damage existing infrastructure, requiring extremely precise explosive management. At the same time, the project faced severe logistical constraints typical of high-altitude alpine construction. All materials, equipment, and personnel had to be transported through a vertical access shaft approximately 38 meters deep, combined with a construction cableway system. Every delivery, every machine component, every worker movement required careful coordination in a completely constrained environment. Meanwhile, a separate upper water conveyance tunnel was being constructed on a different schedule. This tunnel, approximately 140 meters long, was excavated toward Lake Rittm but intentionally stopped around 20 meters short of the water body. Final breakthrough could only occur during winter, when lake levels dropped enough to ensure safe construction conditions. Deep inside the mountain, the TBM had already advanced roughly 300 meters when the next major geological problem emerged. At around 300 meters of penetration into the mountain, the TBM entered one of the most unstable geological zones of the entire project. Although excavation continued, and roughly 12 cubic meters of material were still being removed per cycle, the machine's forward progress began to slow dramatically. This was not a mechanical issue. It was a sign of something far more dangerous underground. The rock mass ahead had started to lose structural integrity. Soon after, the situation escalated. Void formations began appearing above the tunnel crown, indicating internal collapse within the surrounding geology. All operations were immediately halted. Probe drilling was carried out directly from the cutter head to determine the condition ahead. The results confirmed a critical failure zone. The TBM had entered a fault structure composed of heavily crushed rock, trapped between two stable rock layers. Geologists identified it as a crushed shear zone, typical of tectonic faulting conditions in alpine environments. In this type of formation, the rock mass has almost no self-supporting strength. Material can shift, slide, and collapse without warning. And in this case, the overlying strata began to move, increasing the risk of subsidence directly above the machine. Immediately behind the cutter head, the most sensitive zone of the entire system was under extreme stress. This area was reinforced with rock bolts and steel mesh to stabilize the tunnel crown and protect the working environment. But even with support systems in place, the TBM's forward progress stalled. The machine was still excavating material, but the surrounding rock mass was no longer responding in a stable way. Void expansion continued above the excavation zone. Engineers confirmed that the machine had fully entered a fault-controlled collapse zone. Emergency stabilization measures were initiated immediately. Long steel anchors were drilled deep into the surrounding rock mass. These anchors were then secured using high-pressure cement grouting, filling fractures and locking the reinforcement system into the formation. Once the grout hardened, it created a reinforced structural network inside the fault zone. Stabilization work progressed methodically from the tunnel crown down toward the sidewalls. Layer by layer, the unstable rock mass was gradually brought under control. Over a continuous 4-week operation, approximately 13 tons of cement were injected into the formation to consolidate the fractured zone. Only after full stabilization was achieved could the TBM resume operation. Once restarted, the machine slowly advanced through the previously unstable section. To further secure the excavation, segmented steel liner plates were installed directly behind the cutter head. These steel segments provided immediate structural support and created a stable surface for the gripper system to operate against. This allowed controlled forward movement through the fault zone. However, excavation was no longer continuous. Inside this geological zone, the TBM could only advance in extremely short cycles of approximately 25 centimeters. After each small advance, operations were paused. Workers installed additional steel lining segments, removed excavated material, and rechecked ground stability before continuing. Progress became slow, controlled, and highly technical. Every step forward required full structural verification. Because of extreme spatial constraints inside the tunnel, liner installation could not be fully mechanized. Steel segments were positioned using cable winches and auxiliary lifting systems. After placement, crews manually bolted and welded each section to form complete structural rings. Once each ring was completed, cement grout and concrete were injected behind the lining to transfer load into the surrounding rock mass and stabilize the tunnel crown. Across 6 separate fault zones, approximately 85 meters of tunnel were reinforced in this way. The operation required more than 100 tons of steel and an equivalent volume of cement-based materials. This section of the project represented one of the most complex structural stabilization phases of the entire excavation. After exiting the fault zone, the TBM finally re-entered competent alpine rock. Excavation speed immediately increased, reaching up to 20 meters per day. Compared to the restricted 2 5-centimeter advances inside the fault zone, this represented a massive recovery in productivity, but the final challenge still remained: a steep, curved section of tunnel with gradients reaching up to 42 degrees. At this angle, gravitational forces became a critical engineering risk. The entire TBM system was now heavily dependent on the gripper mechanism and anti-rollback safety system to prevent uncontrolled descent. At the same time, cutter head wear had become severe due to prolonged operation in abrasive rock conditions. Manual cutter replacement was required inside the confined and inclined tunnel, adding significant operational risk. Just before final breakthrough, another geological void was detected above the excavation front. Under normal conditions, the operation would have been stopped for drilling and grouting reinforcement, a process that could take several additional weeks. Instead, engineers implemented an unconventional solution. They injected shotcrete directly through the cutter head area to rapidly stabilize the void above the tunnel crown. This was performed using a specialized dry shotcrete system known as LDSB-1N. The material used was steel fiber reinforced dry concrete, transported into the tunnel via the cableway system. Water was added only at the nozzle during application, allowing rapid setting upon contact with the rock surface. This technique significantly reduced dust levels inside the long-confined tunnel and improved visibility and safety for workers. Most importantly, it stabilized the critical area ahead of the TBM, in a fraction of the time required for conventional reinforcement methods. This emergency intervention saved approximately 5 weeks of construction time. Finally, after excavating 1,400 meters through the mountain and overcoming nearly 800 meters of vertical elevation difference, the breakthrough was achieved. On February 23, 2022, engineers and workers gathered underground to celebrate the final connection of the tunnel. This marked the completion of a major underground hydropower infrastructure inside the Swiss Alps. After breakthrough, the project entered its final phase: structural completion and TBM dismantling. Due to its massive size, the cutter head could not be removed in one piece. It had to be dismantled section by section directly at the tunnel face. Each component was then lifted to the surface through the access shaft using heavy hoisting systems. This was a highly complex and controlled operation requiring precision coordination and strict safety procedures. Once the cutter head was fully removed, the remaining TBM backup system was carefully transported back toward the launch chamber. Throughout this process, the anti-rollback system once again played a critical role in ensuring safe recovery along the steep tunnel alignment. With completion of the final water conveyance connection to Lake Rederiksboden, the underground hydropower system was fully completed. A project that began as a modernization effort had evolved into one of the most technically demanding tunneling operations in the Alps. The upgrade of the water conveyance system for the Rayam Hydro Power Plant was far more than a conventional infrastructure project. It stands as a clear demonstration of humanity's ability to confront nature through science, engineering, and perseverance. Throughout construction, Engineers and workers faced numerous challenges: complex geology, high-pressure groundwater, dangerous fault zones such as Cockeright, and the harsh working conditions deep within the Alps. Every meter of tunnel advanced was the result of precise calculations, field experience, and the determination of an entire engineering team. Behind the success of the project lies the combination of human ingenuity and modern technology. Massive TBM machines, hybrid injection systems, steel fiber shotcrete, and safety mechanisms, such as Rikvar-Sikkerung, illustrate the advanced capabilities of modern tunneling engineering. These technologies allowed engineers to design machines powerful enough to cut through mountain rock, yet precise enough to operate in fragile and unpredictable geological conditions. The project also reflects the scale of investment required to sustain Europe's strategic infrastructure. Hundreds of millions of Swiss francs were invested not merely to excavate a new tunnel, but to ensure a stable energy supply for the Gotthard Railway Corridor, one of the most important transport routes across the Alps. Such investment demonstrates a long-term vision for building resilient energy and transportation systems for future generations. Above all, the success of the project belongs to the engineers, technicians, and workers who spent countless hours deep inside the mountain, working in confined spaces, under wet and high-pressure conditions, and constantly facing geological risks. They advanced step by step through rock that had formed millions of years ago. Through discipline, teamwork, and dedication, they transformed engineering drawings into a functioning underground structure. When the Ritum Tunnel was finally broken through in February 2022, it was more than just the completion of a construction milestone. It symbolized the power of human cooperation and ingenuity in solving complex engineering challenges. From equipment flown in by helicopter to massive tunneling machines operating deep underground, the entire project reflects the remarkable creativity of modern engineering. The Ritum project is therefore not just a water tunnel for hydropower generation. It is a story of perseverance, determination, and the belief that through science, technology, and collective effort, humanity can overcome even the most formidable challenges hidden within the Alps. Thank you for watching until the end of this story. If you enjoy content like this, don't forget to like, share, and subscribe so you won't miss our upcoming explorations. Iron Process thanks you for watching, and we'll see you in the next story.